Hello everyone, welcome back. So today we'll learn about learn how to solve trig equations. So our goal is to do that. Then also what can be different about these and only be able to solve it, make sure we can write the solution correctly depending on how and what interval or what range we need the solution in, whether it's just in radians or degrees. And also if we're talking about within essentially one trip around the circle or maybe all possible solutions. So we'll see that. So our directions how to solve a trig equation. What makes it something a trig equation is if your unknown variable, in this case theta, for example, is inside a trig function. That's what makes it a trig equation. Okay, where this angle is unknown. All right. So the solution, of course, is any angle that makes this true, wherever that angle is, in whatever quadrant, or if it's a coterminal angle, however many, possibly could be an infinite number of solutions depending on how the solution is being answered. So the basics is says basically you need to determine essentially the domain of the solution. So it says just solve the equation or find all solutions. That means you have to find every possible solution. That includes, for example, coterminal angles. Okay, but sometimes it may just simply say to solve within 0 and 360 degrees, or maybe within 0 to 2 pi. In that case, just one trip around the circle are all the solutions we're looking for. Okay, so when to solve the equation, we want to find the angle or angles within the unit circle or whatever that make that a true statement. Okay, and possibly want to draw a picture or use unit circle or do reference angle or unit circle values to find the solutions, then write the solutions correctly. So let's look at our first example and kind of, as we do this, kind of figure out how this works. So our direction will just be to solve. And actually for most of these, we'll actually show the solution in different ways as well, in terms of radians and degrees. Let's start with this. So let's say number one, we have the cosine of theta is equal to negative square root of 2 over 2. Okay, now, so we want to make sure that our, so also number 2, solve the equation for the trigonometric function if possible. So the trig function is not by itself. If there's only one, we try to do that first. In this case, it already is. So now let's look at the unit circle. I've attached the unit circle here for easy reference. Okay, so cosine, also we can mention here, that cosine of theta is negative in quadrants 2 and 3. That tells us where to look. Okay, so we're going to get the solution is going to be if there's a solution in quadrants 2 or 3. If you look on the unit circle, remember on the unit circle, the x coordinate of each angle is your cosine value, and the y coordinate is the sine value. So if we look in quadrant 2, 3 pi over 4, the cosine of 3 pi over 4 is negative square root of 2 over 2. And then also in quadrant 3, we also have essentially a related value, essentially like a mirror image. Okay, we often will see that. So here, at this angle, 3 pi over 4. Sorry, I should have put that there. And then also we have a solution for 5 pi over 4. And these two are related. Actually, they're, since they're both essentially pi over 4 from the x-axis. So this one, as I said, is 5 pi over 4. Okay, so those are solutions because that makes this a true statement. If you take the cosine of either 3 pi over 4 or 5 pi over 4, you get negative square root of 2 over 2. Okay, so then our solution, let's think of different ways to write this. So our solution, if I say n maybe 0 degrees to 360 degrees, okay, we're already show them in radians. So that's going to be theta in degrees. We just compare what we got. So look on those angles in degrees. Degrees, those will be 135 and 225. Okay. Now in radians, okay, or instead of saying in radians, we'll just say in 0 to 2 pi. So if you see this indicates you want the answer in radians. Already said what those are. It's basically going to be 3 pi over 4 and 5 pi over 4. Okay. Now, what if it says all solutions? then basically what we do is kind of modify this. So what it means to all solutions is think about our picture again, okay? So basically that includes not only this angle, but any coterminal angle, both positive or negative, okay? So if you go around 2 pi for this one, no matter how many times you go around either direction, as long as you end here, that angle ends here, that angle is also a solution. So the way to write that is basically in degrees, it's going to be theta is equal to 135 degrees plus 360 times k, where k is going to be an integer. Do the same thing for this one. So 225 degrees plus 360 times k. Once again for here. And we also do the same thing for radians, okay? And so it's going to be theta is equal to 3 pi over 4 plus 2 pi times k. And also for the other one, 5 pi over 4 plus 2 pi times k, where k is any integer. Remember, integers are numbers like 0, 1, 2, 3, and they're negatives, okay? So any one of those will give you a solution. That's if it asks for all solutions. Okay. Sometimes it may just ask for solutions in 0 to 2 pi or in 0 to 360 degrees or possibly in other intervals. Okay. Look at our second one. Okay. This time, let's say we have tangent of theta minus 1 is equal to 0. Okay. That's our new one. So here, the first thing we want to do is get the tangent or get the trig value by itself, the trig function by itself if possible. So they say we want to solve for tangent of theta. We do that then, that gives us then tangent of theta equals 1. Okay. Now here, of course, tangent is positive. All right. This is positive 1. So tangent of theta is positive, is greater than 0 in quadrants 1 and 3. So it's where both sine and cosine have the same sign. Okay. So 1 and 3. All right. So let's look at our unit circle. So basically, we're looking for, remember, tangent the same as sine over cosine. So looking at places where the sine and cosine are the same. And that's it basically in terms of degrees, 45 degrees and 225 degrees. Okay. We do this the same way. So if I say in, well, first let's make a picture here. Draw a picture to help us with this. These are related. So right here, I'll start this in a degree. So 45 degrees. Then down here, we have 225 degrees. Okay. So if I say I want my answer in the interval from 0 to 360, then our theta is just going to be those two angles, 45 degrees and 225 degrees. Okay. Then if I say in 0 to 2 pi, it indicates I want the answer in radians. Okay. Then I just use the radian values, pi over 4 and 5 pi over 4. Make sure this is clear. So this is, write that better. So 0 degrees, 0 radians to 2 pi radians. In that case, our theta is going to be, as I said, so pi over 4 and then 5 pi over 4. Now, what if I want all solutions? Okay. Now here we can actually do something a little bit simpler. Now, first off, we can simply do, for example, 45, like we did above, the first example, we can do 45 plus 360 times k, and the second one plus 360 times k. But it's better then if we can actually combine things. Okay. So if you notice, that's one reason why it's helpful to draw a picture. There's something in common these angles have that the first two in the first example didn't. These angles are actually 180 degrees apart, or pi radians apart. Okay. So we can actually collapse both and write one solution. Okay. So what we can do then is we can write this as, well, first off, let's write it out both at the same time. So theta is equal to 45 plus 360k. And theta is equal to 225 plus 360 times k. But we can combine both of these into this. Since they're 180 degrees apart, we can write this as 45 degrees plus 180 times k. Once again, it's where k is an integer. Okay, let's see if that works. So go 45 degrees, we add 180 to it, we get this, okay, 225. Add another 180, go back to the starting point and keep on going that way in a positive direction. Or if we subtract 180 from it, okay, up right here, subtract 180 again, we're back to this one. So we just keep alternating between these two. So we can collapse both these solutions into this, and this makes it much more kind of easier to work with form, okay? And also in radians then, let's say, or in radians, this is going to be pi over 4 plus, instead of 2 pi, plus pi times k. Same thing. So starting here, from pi over 4 radians, go pi, we get here, or we go a negative pi, we get there. And then if we do multiples of pi, we either end up here or here. Okay. So that's a much easier, a better solution because it's simpler. Okay. All right. Take a look at our next one. We'll start a new page, number 3. So we have 4 times the sine of squared of theta minus 3 is equal to 0. Okay. So once again, I want to solve for the trig function, solve for sine squared of theta. So add 3 to both sides. We have 4 sine squared of theta is equal to 3. Okay. And then divide both sides by 4. So we have sine squared of theta is equal to 3/4. Okay. Now, here, we want the answer is sine of something. Okay. So basically, essentially what to do is use something called the square root property. And what that means is that basically it's kind of like taking the square root of both sides. So if the square root of theta is equal to this, make sure this looks like a 3. Write that better. Then essentially if we take the square root of this becomes just sine of theta. And here, of course, this is going to be the square root of 3/4. But we need a plus or minus out front because if we square either one of these, we square either positive or negative, we get a positive. So either one of these could be a valid solution going backwards. Okay. And of course, then this becomes just sine of theta is equal to plus or minus the square root of 3, take the square root of both over 2. Okay. Now here, basically, since we have a plus or minus the unit circle, what we're going to have then, as we'll see, is basically we're going to have a solution in each quadrant. Because it's plus or minus, and basically sine is positive in quadrants 1 and 2, but negative in quadrants 3 and 4. All those are equally valid, so I actually have a solution in each quadrant. So let's draw a picture. So now, once again, look and see each quadrant in which what angle gives us a sine or a y-coordinate, square root of 3 over 2. And we see, so in the first quadrant, okay, that's going to be pi over 3. All right, in quadrant 2, that's going to be 2 pi over 3. In quadrant 3, that's going to be 4 pi over 3. Gives us a negative that value, negative square root of 3 over 2. And then finally in quadrant 4, that's going to be 5 pi over 3 in radians. Of course, in degrees, we'll see this as well. Okay. Now, once again, we have 4 solutions. Okay. So if we want our solutions in degrees, 0 to 360 degrees, okay, then we have 4 of those. So that's going to be 60, 120, 240, and 300. Okay, so those 4, 60, 120, 240, and 300 degrees. Okay, now, want our solutions in radians from 0 to 2 pi. ones we just said. So wherever theta there in the room, so pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Okay. Now, if we want to do all solutions, then let's do this in both radians and degrees. Now here, once again, we can actually combine a couple of these. Okay. So if you notice, pi over 3 and 4 pi over 3 are pi apart, or 180 degrees apart. So we can say, for example, pi over 3 is the same as 60 degrees plus 180 times k. That gets this one and this one. Okay. And then if we start here at 120, which is 2 pi over 3, we can do 120 plus 180 times k, and that gets these two. Okay. Once again, where k is any integer. Okay. Then I can say, or if you want to do it in radians, we have theta is equal to pi over 3 plus pi k, and theta is equal to 4 pi over 3. Oh, sorry, not 4 pi over 3, 2 pi over 3 rather. Plus pi times k. Okay. Now you might be wondering, could we combine all four into one? Unfortunately, not in any easy way, because although these four solutions, if you try to do like every pi over 3, then actually you'd end up, if I do like, add pi over 3 here, that would get this one. And another pi over 3 is going to be at actually pi, 3 pi over 3, and that's not a solution. So unfortunately, we can't really combine all of them into one. Okay. A few cases might be able to do that, but in this case, we can't. Okay. Let's see what's next. Okay, number 4. Let's have the cotangent of theta is equal to -1. And let me check something here real quickly. Okay, so here, all right, that's already by itself. All right, the free function is already by itself. Now here you can do a couple things. You can also write this in terms of tangent if you want, or use cotangent directly. I'll write this in terms of tangent. Okay, of course, cotangent is 1 over tangent of theta is equal to -1. Okay, now if we can flip both sides, so one thing you do with an equation, you can take the reciprocal of both sides at the same time. That's also the same equation. So just flip both sides. This would be tangent over 1, or just tangent of theta, and that's going to be over -1 over itself. It's just going to be 1 over -1 is still -1. Okay, of course, tangent of theta, where is it negative, less than 0 in quadrants 2 and 4, basically where sine and cosine have opposite sides. Okay, so if you look over once again at our unit circle, we know we're going to have a solution, one in quadrant 2, one in quadrant 4. Then basically, where essentially are sine and cosine the same except opposite signs, and that's going to be in terms of either degrees or radians, which we want to use, 135 degrees and 315 degrees. Okay, you have one solution here that's 135 degrees, and here that's 315 degrees. Now, once again, these two solutions are actually, so we just do we won't show it this time, but we just simply do this in degrees, 0 to 360 degrees, then those are our two solutions. Okay, theta is equal to 135 and 315. Okay, now if you want to do it in radians, then it would be in 3 pi over 4 and 7 pi over 4. And then once again, if you do all solutions, you combine these into one because they're pi apart. So you do that in the same way. Okay. All right. Now let's take a look at some that are a bit different in the sense that the way we approach them. Okay, good. is a bit different. The way we solve is a bit different. I'm just going to do a new page. It's number 5. So this time we have, let's say we have 2 cosine squared theta plus cosine theta minus 1 is equal to 0. Okay. Now, this obviously is a bit different. Okay. Involves 2 trig functions. So we can't really get one trig function by itself in the same way. Okay. Hopefully this looks somewhat familiar. And actually what we're going to do is use a substitution. This is something you kind of saw done in calculus and other areas, just to make things simpler. We're going to say we're going to let, called a u substitution, let u equals the cosine of theta. This is often useful in cases like this. It's not required. What I'm going to do then, wherever we see a cosine, I'm going to put u. Okay. And so that's going to give me then 2 have cosine squared, that's u squared, plus cosine theta is u minus 1 is equal to 0. Okay. Now, why is this valuable? Well, now I have a quadratic equation. It's more clear. You kind of see it here. As you practice this, you kind of skip this step, but this is useful. Now, this can either factor, use a quadratic formula. I'll just factor it, but of course, you can always use a quadratic formula. If we factor it, then what we're going to get is x u plus 1, u plus 1, and 2u minus 1. Okay, we factor that. If you're unsure, FOIL this back out and make sure you get the same thing. Okay, now remember, if you have a product or factors multiply together, remember a solution is anything that gives you a true statement. So if either one of these factors is 0, it makes this side 0, makes this true. So to figure out which makes each one 0, so if u plus 1 is equal to 0, that will give us one solution. And then 2u minus 1 equals 0 will give us another solution. Of course, this is u is equal to -1. And over here, this obviously is going to be, if you solve it for u is equal to 1/2. Okay. Now we're going to substitute back, okay, in terms of cosine. And so that's going to give us 2 equations. Cosine of theta is equal to -1. And the cosine of theta is equal to positive 1/2. Okay. Now, let's take a look what our solution. So, of course, cosine. So, where is cosine negative? Cosine is negative, and basically, I'm going to write this up. Cosine of theta is less than 0, is negative in quadrants 2 and 3, basically on the left side of the y-axis. Okay, so if we look at solutions there, whereas cosine -1, actually in one spot, actually at pi. Okay, so here for this part, theta is equal to pi. All right, so we draw this. We have one solution at pi for this part. Now over here, cosine, this one is positive, so cosine theta is obviously positive than the other 2 quadrants in 1 and 3, 1 and 4. Okay, so look for where cosine in quadrants 1 and 4, where cosine or the x-coordinate is 1/2, and that's in terms of degrees, and we're actually in radians right now, pi over 3 and 5 pi over 3. Okay, so there we have theta is equal to pi over 3 and 5 pi over 3. Okay, so over here, pi over 3, and then down here we have 5 pi over 3. So this equation actually have with 2 equations, we actually have 3 solutions. Okay, and so here we'll just do this in radians. So we'll say n 0 to 2 pi, and we have 3 solutions. We have pi over 3, pi, and 5 pi over 3. So you plug any of those into this equation, and that will give you, make that side 0, give you a true solution, give you a true result. Okay, and then once again, you can also, essentially add 2 pi over k, 2 pi times k to each one of these, get all solutions, or also put them in terms of degrees if you want as well. Unfortunately, these can't really combine since there is no really common factor in between them easily. Okay. All right, let's do 1 or 2 more. Okay, so I'm up to number 6. Okay, this time we have cosine squared x minus sine squared x is equal to 0. Okay, once again, I have two functions. Now, some of these ones have like two trig functions like this, and sometimes it's hard to make up a really good rule for saying always what to do. Sometimes this just takes practice and also takes experimentation, sometimes to figure out the right path. Let's take a look at this. So actually what I'm going to do is first off, I have two different trig functions, unlike the one I had before, both in terms of cosine, this in terms of cosine and sine. So I'll say get both in terms of one trig function. That's a good idea if possible, if you can do that. So what I'm going to do actually here is actually I'm going to write this, use a Pythagorean identity. This is the same as 1 minus cosine squared of x. Let's do that. And so we have cosine squared of x minus, now use parentheses, I'm subtracting this whole thing. 1 minus cosine squared of x is equal to 0. Okay, we distribute that. And so we have cosine squared of x minus 1 plus cosine squared of x is equal to 0. We have combined our like terms of cosine, so then we have 2 cosine squared of x minus 1 is equal to 0. Okay, a couple ways we can do this. All right, and making me think, if it's better. I had made one, in fact, here is a good example. I had in my mind one way to do this, but I'm thinking it might be better to do it a different way. Give me just a moment here, I think. Actually, let's just do this in kind of we did number, I think our example is number 2 or 3. Let's get cosine squared by itself, so I can write better. Cosine squared x, not theta, sorry. Cosine squared x by itself. Okay, and so if I do that, then if I add 1 and divide both sides by 2, I have cosine squared x is equal to 1/2. Okay, now, once again, since you take the square root of both sides, this gives me then cosine x is equal to this plus or minus the square root of 1/2. Now, that's going to be plus or minus 1 over the square root of 2. If you rationalize that, multiply the top and bottom by 2, then that's going to give us finally cosine of x is equal to plus or minus the square root of 2 over 2. Okay. Now, that's the value we've seen on the unit circle. Okay. Now here, once again, like the previous one, I have a plus or minus here. And so, of course, cosine is plus or minus in each one of the quadrants. So once again, we're having a solution in every quadrant. Let's look at that then. Like this one is going to be kind of interesting. So if you look, and let's do this in degrees this time, though it doesn't matter. So we're going to have a solution at a positive solution where it's positive square root of 2 over 2 at 45 degrees. Okay. Other than where it's negative square root of 2 over 2 at 135 degrees. Okay. Then down here in the third quadrant, one where it's also negative at square root of 2 over 2 at 225 degrees. And then finally, another one where it's positive at 315 degrees. Okay, so if we look for solutions in 0 degrees to 360 degrees, then we just have these 4. So 45, 135, 225, and then 315. Okay, but now let's do an all solutions case, and this is interesting. Okay, and we'll just do this. Of course, you also do this in, could very well do this in radians. We'll just do this in degrees. Okay, the nice thing about this one is actually these we can actually combine. Okay, we can actually combine all 4 of those, and certainly if you do 45 and 225 or pi apart, you can all, so let's back up. You can do all 4 separately, add each one plus 360 times k. You could also, these two here obviously are pi apart, and these are, or sorry, these are 180 degrees apart. Make sure I'm doing this in degrees. These two are 180 degrees apart, so you could do like 45 plus 180 times k, 135 plus 180 times k. The nice thing about these are all 90 degrees apart. You go from 90 degrees from here to here, you get this, and 90 degrees here, and then 90 degrees here. So actually, we can collapse all four of these solutions into just one. So this is really useful here. So now our theta is going to be, in terms of degrees, 45 plus 90 degrees times k. Once again, k is any integer. Okay. And I'll also do it in radians as well. Or they is equal to pi over 4 plus, of course, 9 is the same as pi over 2k. Okay. So this is nice thing. We can actually collapse all four of these solutions for all possible solutions into just that. Okay. Let's wrap up with one. I guess I'm on what number am I on? 6, number 7. One we have to do on a calculator. So we want to solve 2x times the cosine of x equals 0.7 on a calculator. Okay. The reason we do it on a calculator, because actually this is something we can't actually get x by itself. There's no way to do that. Okay. So what we're going to do then is we're going to graph on your graphing calculator. Actually, we're going to use Desmos. We're going to graph for 1, let's call it y1. We're going to graph the left side, 2x times the cosine of x. Okay. And then for y2, we're just going to graph the right side, okay, 0.7. And also, we're going to do this in radian mode. Just be careful what mode you're in. Okay. And then solutions are the x coordinates of the points of intersection. Okay, so the places where these two intersect, those are our solutions. Now let's look for solutions. Specifically, we're going to find solutions in 0 to 2 pi. Because actually you can also, there are kind of infinitely many solutions of this, but we're going to do those in 0 to 2 pi. Let's graph this. Let's do this on Desmos. And we're going to be using dsmos.com. Okay. Now, it is default in radian mode. If you want to check, click on this wrench over here. And it's in radian mode. I'm going to change the degrees. Let's click on degrees. We want this in radians. Okay, just click on the screen anywhere to get rid of that. Then let's graph that. So it's 2x times the cosine of x. Okay. Next, we zoom out. This goes on forever. And so, as well, it turns out there actually be infinite number of solutions. If you did all solutions, it'd be kind of hard to, a little more complicated to actually find all of them. We're just going to do the ones in 0 to 2 pi. Okay. In fact, let's just label 0. Let's label 0.2 pi and 0 just so we know where to stop. Okay. So we're going to go from 0, 0 to this point. Okay. Find the solutions. So let's zoom in a bit. Oops, I haven't graphed the other point yet. Sorry. So graph a 0 point. So y equals 0.7. Just have to do y equals that. Yeah, there we go. Okay. And also do y equals here, though it's not completely necessary. Okay. Now, so starting from 0, 0 to this point right here, we actually have 3 solutions, 3 places where it intersects. Okay. So, in fact, let me, hang on, I need a pencil so I can write that down. So it's the x coordinate of the point of intersection. Okay. So one intersection is x equals 0.376. Another point is 1.298. And the third one in this range, you see there are more on either side, but just in that range, is 4.786. Okay, so those are approximately our 3 solutions in that range. So once again, what we're doing here is showing that where these 2 lines intersect, this line and this line, so the left-hand side, the right-hand side, where they intersect are the solutions. I can't really find, it's hard to find exact solutions, maybe even impossible, but we can approximate them this way. Okay, so what's going to be chosen 0 to 2 pi, and in that range, there are 3 solutions. So here, 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 and here. And that's what we're going to use. Okay, let's go back. So let's write those down. Okay, And so in that case, then your x is equal to, we said 0.376. Then no, next one's 1.298. And then the third one was 4.786. Okay. And those are our three solutions in 0 to 2 pi in radians. Once again, these are all in radians. Okay. All right. So what we've learned today is how basically to solve trig equations. So basically, you get if there's just one trig function, get it by itself, then use the unit circle to find out where, within the unit circle, using degrees or radians, where how many solutions you have, and then be able to write that in terms of either radians or degrees, and also in terms of all solutions necessary, and also be able to collapse those into a simpler form if we can do that. Thank you. Have a good day.